So my talk is on logic-compatible gain cell EDRAM, and I'm going to present this to you, what it is, and have a look at whether this is a real alternative to SRAM for caches and other applications. So the motivation of this work that we've been doing since quite a while is that if you look at any kind of large microprocessors or any kind of chips that you have in high-performance computing, but also in low-power systems, IoT systems, and so on, very often you find that the area of these chips and thereby the cost is dominated by memory. But not only that, more important in low-power systems, of course, is the power consumption. And there is clear that very often memory is actually responsible for 50% of the power during active state, and actually even 100% during sleep state, because if you need a state-retentive sleep, well, the only thing that's going to be on is the memory, and that's going to leak, and that's where your power goes, right? So there need to be something that we can do to reduce that, and looking at memory is apparently, the best way to address this issue. So what's the problem here? Well, memories, since a while, memories are actually built from the same kind of structure for a very long time, at least on-chip memories. Right? We usually use this 6-transistor SM cell, and that's our workhorse in memory design. Now, unfortunately, this 6-transistor cell has a few disadvantages. The most obvious one, we need 6 transistors to store a single bit. And then also there's a considerable amount of static power because we have a leakage path from VDD to ground that's basically just blocked by a single transistor. And that leads us to a lot of leakage. In addition to that, that memory cell is based on ratioed operation. That means sizing of the different transistors and also their drive strength, which is influenced by variation, is what basically determines the reliability of these memories, and that causes the fact that when you have embedded memories, you can typically not scale the power below 0.6 or 0.5 volt without having any serious reliability concerns. Also, you have a single access port typically, even though we have 2 bit lines. We can just read or write at the same time. If we want to do read and write at the same time, we need even 8 transistors or even more. So what can we do? Well, we can think of different memory structures, and that's not all completely new. But I want to renew the thought of having dynamic memories, which we know as the workhorse of off-chip memory, but we want to do this on-chip. So how do we do this on-chip? Well, basically the idea is the same as off-chip EDRAM. We are using a charge-based storage model, and we need 2 access networks, one for the write and one for the read. And these 2 access networks we can realize in different ways, typically with 1 or 2 transistors. And if we can do that, well, if we have 2 transistors in each one of them, well, we'll have only 4 transistors or even fewer, down to 2 transistors, so we have more density. And also in this kind of structure, we don't necessarily have a direct path between VDD and ground because we don't have a voltage supply hooked up to the memory cell itself, at least not directly, only through the drivers of the different bit lines. And that would cause us less leakage power. So the first way to apply this is in a DSP application where very often we have small memories that are distributed across the chip, small chunks of memories that get written and rewritten all the time, so you don't need to retain the data for a very long time in those memories. That's a very typical case. So one example I'm going to give you for this is a test we did some time ago on a typical DSP application in communications. That's a circuit that does error correction coding. And in those circuits, as I said, you have a lot of small memories, and we realize them actually based on latches and standard logic, so we call those standard cell memories. They're very good because they turn out to reduce the dynamic power of the memories inside these DSP circuits by almost 50%, and that's known by a number of people. The disadvantage is obviously that these circuits, they are relatively large because we use latches. So the obvious way, given that what I said before, we can simply replace the latches by using dynamic latches, which have this dynamic storage mechanism and are much more compact. So you see one of these here, where we use another a transistor as a MOSFET to increase the storage capacitance, so that we can guarantee that we can retain the data for the amount of time that it's needed from writing it to reading it to writing it again, right? Which is a rather short time. So this works pretty well and actually gave us a reduction in the area of about 44% of the entire system, which is quite good. So we were able to recover this. But that's a special application. Typically, we would like to do memories in large chunks or in larger macros. So in order to do that, we need to just have a simple look again at the structure that I showed before. We need to find a bit cell, and on the left you see typical 6-transistor SRAM bit cell. And on the right, you see two of the smaller realizations of the gain cell. First one is a 2-transistor gain cell. The second one is a 3-transistor gain cell. And both of them you can realize with about half of the area, if you look at try to make a compact layout of that, of an SRAM cell on the left-hand side. So that's a very good idea. Gives us a lot of area advantage and can be realized in a very compact form. Now, if we want to put these into a memory array, well, we need to architect the array around it, and we can do different forms of this. But essentially, what you see on this slide is the structure of a typical EDRAM, on-chip EDRAM memory array, which is very similar to what you would have in a larger scale SRAM, where you basically decompose the memory into smaller subarrays. This you need to do because otherwise you will get bit lines that are way too long and that are difficult to charge and discharge. So you break it down into subarrays. Each one of these subarrays has a number of rows, typically 128 or 256 rows. And then you multiplex them. You have a read access and write access logic. You read and write bit lines that run across these memories. Now, how would this work? I give you a simple example of simply using a 2-transistor bit cell. There's similar examples for 3-transistor bit cells. I'm going to use the example on the lower left. You can build the bit size, the bit cell from different types of transistors, from NMOS and PMOS transistors with different threshold voltages. Which one you use changes the trade-off between access time and retention time, because PMOS, for example, leaks less than an NMOS transistor, high VT transistor leaks less than a low VT transistor. So you can do different combinations. I'm just going to use the example on the lower left, where we have an NMOS write access transistor. If we need to write in the cell, we provide the right word line with a boosted voltage in order to be able to transfer reliable levels on our storage node through the write bit line. If we want to do a read, well, you find the read bit line that you also have in an SRAM and the read word line. The read word line basically so we first pre-discharge the read bit line, and then we apply a pulse through the read word line, and that basically is what addresses our memory. Depending on whether the read bit line gets charged or not, that determines whether there was a 1 or a 0 inside this memory. So that's the basic functioning principle of our small cell, of our smallest possible cell that we can realize. Now, as I mentioned, the problem of this is that we will basically need to refresh those memories, and the difficulty is to see how often we actually need to refresh those memories. So in order to understand that and whether that makes any sense to implement that in a typical process and allows us to replace a typical SRAM with one of these gain cell EDRAMs, let me give you an example. So if we want to figure out what is the availability, because that's what matters to us, right? We want our memory to still be available, even though we need to insert or inject some refresh cycles. We need to figure out what the cycles is in terms of percentage that is covered by refresh. Well, in our case, I said we have a read and a write port that we can exercise in parallel. That means that the refresh can be done in a single cycle if we overlap read and write cycles, read and rewrite cycles basically in a row. So we can overlap those. So we need a single cycle for a refresh for each one of these rows. And as I said, the memory array, the larger memories are broken down into subarrays, say with 128 lines. So if I give you an example, a typical EDRAM would have a retention time between 100 microseconds and about 1 millisecond. That's something that from our experience we can say we can typically realize. We have a typical access time that is way below 10 nanosecond, but let me assume we have a 10 nanosecond access time. And we would have a subarray size with 128 to 256 rows. So if you do the exercise, you do the math with those numbers, you'll find out that you have an availability of about 98%. So if you want to realize these memories, if you have this availability, and you would think of a typical IoT SoC where you would have a structure that looks like the one shown in this picture with the L2 memory that is separated from the cores with a number of caches and with the bus, and that is controlled by a separate memory controller that could take care of the refresh operation. You would notice that actually this memory is not all the time busy. So if we assume that we have a 98% of that availability of that memory, that will not really impact the operation of this overall system, which makes this structure very viable. So if I summarize some of these results, we believe that using gain cell embedded DRAM is actually a real alternative to SRAM, because they have a small cell size and they are much better than one transistor, one capacitor standard DRAMs, for example, because we don't need to care with these problems that we have due to a destructive read, which you have in the standard DRAM. We don't have that, so we can read as often as you like. We have a natural two-port operation that also helps us in the overall system context. We can have a lot of potential to operate the read and write ability because both of them happens through different networks. So we can do that, and we can find trade-offs between the retention time and the actual operation. Now, because there's a number of advantages, there have been several use cases of this reported in the literature with different cell structures that you see around here and in different technologies. And if you wrote this, there's no roadmap which basically shows a number of papers that have reported eDRAMs. You see that these eDRAMs have been realized in various technologies from 180 nanometer all the way down to 65 nanometer, and that's essentially where it stops. Now, the problem is, of course, that technologies become more and more leaky as we are going to advanced technology nodes. And this is what you're going to see. Basically, on the left, you see the charge decay inside the cell, right? And you typically have one level inside the cell that decays much faster than the other one. Now, can we do anything? Because if we cannot provide a solution that allows this eDRAM, gain cell eDRAM to work in 28 nanometer and below, that's going to be a difficult issue. Now, it turns out that by simply adding one or two transistors, well, two transistors in the case of the 2T cell, so we're ending up with a 4-transistor cell, still smaller than the 6-transistor SRAM cell. We can add a feedback inside the cell that supports the weaker level of the two, and basically allows us to retain a good retention time even in 28 nanometer and below. Example of this basically is shown here, where we've realized the test chip in 28 nanometer FD-SOI, and you can see that the cell size is actually quite a bit smaller than still quite a bit smaller than the SRAM. This comparison here is based on a redrawn SRAM cell in standard technology rules. So there we see a significant advantage. If we compare the array size, we still see an advantage. So we are about 17% better than the SRAM provided by the foundry. What you have to take into account here is that the SRAM provided by the foundry has special push design rules that we are not using in order to design our eDRAM cell, which could be made significantly smaller doing these pushed rules. Last advantage that I'd like to point out, if you look at the power, we have to look at the retention power. And for an SRAM, the retention power is the leakage from VDD to ground. For our eDRAM, the retention power is the power that we require to keep refreshing the memory. So that takes into account the need for a running refresh, which is in the end ends up being lower than for the SRAM, which tells us that this also gives us an energy advantage. Now, this is the standard area of application. I want to, before I conclude, give you an example how this can be brought further. As you've noticed, still, even though we solve some of these refresh issues, for example, with this special cell, refresh remains an issue. And one of the problems there is that in an overall array, the refresh time needs to be set according to the worst case cell in the arrays. Now, if you look at the retention time spread in those arrays, you get what we call the retention map. That's this colorful picture on the left, which basically tells you the retention time of each cell. And on the very left, you see the spread of those. And what we see is that this retention time has a large or long tail. And we need to really be on the left of this long tail in order to be safe. However, if we relax our refresh constraint a little bit so that we are able to successfully keep the data in most of the cells in the RAM, and we are only losing a few of them, we may lose a few bits, but we can actually significantly relax our refresh rate. If you're dealing with applications such as image processing, that may be possible. So showing you an example here where we basically set the refresh time to 1 microsecond, 5, 10, and 50 microseconds, you see that the quality degrades, but at the same time, also our power becomes lower. And if we make an example where we put the quality of the image in PSNR on the x-axis and the retention power savings on the y-axis, you see that even when we retain a PSNR of about 40, 50, 60 dB, we can get a significant amount of power savings. And to give you a feel, a 60 dB PSNR is really a very high image quality that's somewhere between the 1 and the 5 microsecond figure. So overall, to conclude my talk, of course, memory is really one of the main bottlenecks, and we should still think of what we can do there. The 6-transistor cell has a lot of limitations. terms of the power, the area, and also the ability to sustain voltage scaling. I haven't spoken about this, but it turns out that gain cell EDRAMs are very voltage scalable as well. They provide an area advantage. We can hide the refresh in many applications. We can also apply techniques from approximate computing to even further reduce the refresh power. They are very area efficient, and we believe that they are a very good alternative for many applications, especially as they are fully compatible with standard CMOS processes. So none of this requires any additional process steps. That's the end of my presentation. Thank you very much.
We have time for a few questions.
Okay, thank you. Sorry? I'm Sebastian Turiez from CA in Grenoble. So actually I have two questions. The first one is, what is the nominal power that you put at your input of your bit cell? Is that this?
This one runs at 700 millivolt.
Nominal voltage that you need to power your bit cell?
Yeah, that's 700 millivolt in this case.
Okay.
The nominal voltage we need to run the memory.
Okay.
Is that the question? Yeah.
That was the question. And the second one is, you made comparison with the FDSY technology. So did you try to apply some back biasing techniques, trying to reduce the nominal voltage and to apply some RVT or VT compensation by SY?
Yeah. So actually, this one is no body bias, but of course, body bias is an interesting knob because you can tune basically the threshold. That also means that you have a handle on your retention time. You can boost your retention time. You can improve your access time. Unfortunately, these two things are opposite goals, right? But yes, you can play with that, and actually we are currently doing that. It's just not in this presentation. But, thank you. Yeah.
We have time for more questions.
Hello, this is Kai from University of Southampton. Notice that your proposed schematic, you connect the two NMOS to the WWL control signal. I think one of them can be cancelled.
Sorry, which one?
I mean
In which schematic?
Yeah, there's 440.
Oh, in the 4T cell?
Yeah, the NB or NB can be removed because it looks like redundant.
No, actually you can, well, that would be nice if we could remove it. Unfortunately, we could not because then you will shorten. So one of the parts why this is actually working is because the gate and the drain of this of the keeping transistor are separated by an NMOS that is closed usually. So.
Okay, so it looks like a level restore technique feedback and put more charge into that node. Yeah, so.
It will put more charge into this intermediate node. So.
Yeah.
Yeah.
Okay, so but still it's dynamic. Does it still need to be refreshed?
It's still a dynamic cell and it needs to be refreshed. So the one that is actually here is using exactly that 4 transistor cell. It's just flipped. So so it uses that one and needs to be refreshed. You can see we achieve retention times of above 1 millisecond at 27 degrees, and obviously that one goes down as we are going to 85 degrees. So we're 154 microsecond at 85 degrees. If you would do normal, you can see what the 2 transistor cells are in this region. They're much, much below. Okay. So we get a significant boost in the retention time that is key to be able to do it, but still we need to refresh.
Yes, thank you.
But in a typical array, this would end up, for example, in this 1 or 2% refresh rate, right? The calculation was done with the assuming 100 microseconds.
Any more questions?
Yes, so I'm Saïd from Ethos. Are you aware of the last CPU presented by IBM where they claim to have an EDRAM level 3 cache?
They have an EDRAM in it as well, in the caches.
Yes. They are using
to my knowledge, they use 1T, 1C with trench capacitors. Okay. That's my understanding of it.
And so, with comparison, with what you present.
So I don't have a comparison with that one, but if I'm not mistaken, which at least some time ago was not the case, the IBM caches.
It's a public presentation at the last.
I know, but my understanding is that they require special process steps to do the capacitors. We don't. So I'm not aware what I'm not aware what their retention time is, but for sure it's a different technology that's not available, and this is standard CMOS, plain CMOS.
Let's thank the speaker once more.